Okay, so good morning, good afternoon, good evening, everyone. This is the 10th online seminar on nonlinear water waves. Thank you very much for joining us today. I'm the chairperson for today's seminar, Sunao Murashige from Ibaraki University. Today's speaker is Dr. James Duncan from University of Maryland. The title of the lecture is this: Droplets Generation by Plunging Breaker Water Waves. Okay, so Dr. Duncan, could you start, please?
Okay. Well, thank you so much for inviting me. Thank you for your introduction, Sunao. And before I get started, I'd like to acknowledge my students, Martin Aranen and Sophie Wang, and my colleague, Shinan Liu at the University of Maryland, who did a lot of this work. The work supported by the US National Science Foundation. And our most recent grant is a collaborative grant where we're working with Professor Leon Shen at the University of Minnesota. He and his group are doing computational fluid dynamics results to try to predict the results we have from our experiments. Right, I'm having a difficulty. Let me try. It's not changing screen. I think I'll stop.
No, yet. Yes. Could you
Let me try that. Oh, there we go.
Oh, yeah, it's okay. It's okay. Yeah.
Now it's all right. So ocean spray, as everybody knows, I think has a significant impact on the interaction between the atmosphere and the oceans. The spray consists of droplets, and they're typically generated during wave breaking with the influence of the wind as well. And the droplets can greatly enhance the air-sea transfer of mass, momentum, and heat, partially because of the increased surface area you get when you break up the water into these tiny droplets. The droplet by generation by wind waves has recently been reviewed by Fabrice Verone at the University of Delaware. And there were a couple of reviews before that as well. The typical studies in this area take a given height in a wind wave situation, either in the lab or the field, and measure the droplet diameters and perhaps the droplet speeds as a function of wind speeds and at various heights. And there's a number of these studies, and I've just listed a few here. I don't really have time to go into them, but I just want to point out that these studies do exist. There are also a number of fundamental laboratory studies which examine, for instance, the generation of droplets as bubbles rise from below and burst at the free surface. And a number of studies in that area are listed as well. And in our present study, we've got 4 phases of work that we're doing. In the first phase, we're making spatially and temporally resolved measurements of breaking wave profiles and droplet characteristics for mechanically generated waves in clean water. And in our second phase, we're going to repeat many of the measurements in phase 1 with surfactants in the water, soluble surfactants. And then in the third phase, we repeat again, but this time augment the waves by wind. We have a wind tunnel on our wave tank. And finally, if we have a chance and we have the emotional courage, we're going to put salt in the water and see how that affects the droplet production. That's very hard on the laboratory, so we may get to it. The purpose of the combined profile and droplet studies is to determine the breaking processes that generate the droplets and the droplet characteristics associated with these processes. And in our recent publication from the phase 1 work, where we're just doing one mechanically generated wave, we have identified generation mechanisms for a mechanically generated plunging breaker. We have 2 additional papers that we're writing now describing the rest of the phase 1 results. And in today's seminar, I'm going to describe and discuss the results from these 2 proto papers. The results stem from measurements of profiles and droplets for 3 mechanically generated breakers in clean water, as I'll show you in a minute. Whoops. So this is a diagram of our wave tank. It's about 15 meters long, and we operate with a water depth of 0.91 meters. The tank has a width of 1.1 meters into the page. And on the right-hand side, there's a wave maker that oscillates up and down. It's a servo motor position and velocity controlled device that can make very repeatable motions. In the middle of the tank, I show an instrument carriage, in this case, producing a laser light sheet from an argon ion laser. And the water is colored green here because it has a tiny bit of fluorescein dye in the water. And where the light sheet enters the water surface, the dye glows. And I'll show you how we use that in a minute. The wave maker is highly repeatable, as I said, and we generate our breakers from dispersively focused wave packets, which I think is a familiar technique where you produce high frequency waves first and lower frequency waves as time goes on. And as they propagate along the tank, they catch up with each other until you have essentially one wave left. And that wave has all the energy of the initial waves that you generated in the packet. And you can make it so that that wave breaks. We have 3 breakers. The wave generation differs only by the overall amplitude of the wave maker motion. The frequency content and the relative amplitudes of the components are all the same, just the overall amplitude changes. We have 32 components, and the mean wavelength of these 32 components is 1.2 meters. A frequency, the mean frequency, 1.15 hertz. And by linear theory, the phase speed would be 1.36 meters per second. The 3 amplitudes we call the weak, the moderate, and the strong breakers. And in the data and plots that you'll see later, the color coding tells you which it is. The green is the weakest and the red is the strongest. This is a sketch of the tank shown in 2 views. On the left is an end view of the tank. And you can see up on top the laser light sheet being generated, in blue, shown here and coming down in the water and glowing as it enters the water. And over here in the plan view, you can see the laser light sheet coming across the tank. There are several cameras involved. This one camera is actually 3 cameras, and it's photographing the intersection of the light sheet and the water surface. So it gives the shape of the wave along the light sheet. And this light sheet is 1.2 meters long in the center plane of the tank. And also shown here, but I'll discuss later, are the cameras used to measure the droplets. They're horizontal, as shown here, and there's a light beam that goes directly into the camera. And as I said, I'll talk about those in a minute. The breaker profiles are measured by cinematic planar LIF at 650 pictures per second. Images from 3 synchronized cameras are used to create a composite frame, which is 7,200 pixels wide over a field of view of 1.3 meters. And that gives us 0.818 millimeters per pixel. So it's pretty good resolution. The measurements continue for 2.2 wave periods after the breaking starts. The droplets are measured with our inline holographic system at the same frame rate as the profiles are taken. And at each measurement location for the droplets and for each profile history measurement, 10 realizations of the breakers are taken. So just to get you started on what this all looks like, this is a movie, not with the laser-induced fluorescence method, but just with a white lighting. The back of the tank, which is shown here in these different movies, is a translucent surface, and behind it are floodlights. In this picture, you can see the 3 of them here. And the camera is photographing the breaking event in different views. So I'll try to start that. There we go. And you can see the plunging jet hit the water surface and a splash up comes up. And then that splash hits the water surface and creates a second splash. And if you look on the back face of the wave, like here, you can see bubbles popping at the surface on the downstream side of the wave. And then a second wave crest comes by, a non-breaking wave crest. And if you look in the lower right corner, you can see there are many bubbles under the water which are coming to the surface and popping. So I'll let it go one more time. And if you look down at the lower image, you'll see the splash come up, and then suddenly droplets go up into the air here and then up here in the leading edge. I want to emphasize that the droplets that you see in this movie are large, and we're measuring them down to 100 microns in diameter, and there are many more of those smaller droplets, and they're not visible in these images because the pixel resolution isn't sufficient. Okay. So there we go. So this is a laser-induced fluorescence movie of the wave. The light sheet enters the water surface here, and this is the center plane of the tank. So there's no interference with the sidewalls of the tank at this point. And this is an LIF image from a single camera, and there were 3 side-by-side cameras, remember, taking a single snapshot, a single 3-image snapshot of the wave profile. So we have developed some software to find that high gradient of the intensity of the image, which locates the surface of the wave where the laser light sheet enters the water. And we get profiles at each instant in time. If we analyze all the images, then we get 650 profiles per second, but we don't always do that. So this is one of the results. This is just the crest region, showing the profile of the crest between the times when the jet starts to form and the later time when the jet impacts the water surface. And the top one is what we call the moment of jet formation. And that's the first time that there's a point on the front face of the wave where the tangent to the surface is vertical. And a few images later, you'll be able to discern the jet coming out of the crest of the wave. The second one is at a later time, and this is the point when the jet impacts the water surface. So one thing that you can see about these profiles on the right, this is one wave maker motion. This is the strong breaker. And you can see that the profiles look similar in shape, but they're displaced from each other horizontally. And the wave is propagated about 6 meters along the tank up to this point. And the difference in position of this profile and this profile is about 2 centimeters. So there is a little jitter in the device, and we believe that the reason for this is most likely residual motions of the water in the wave tank. We wait an hour between runs. We very carefully control the water quality and surfactant levels in the tank using a Langmuir trough to measure surfactants and keep everything clean. But the thing is that we make a wave about every 30 minutes, and given lunchtime and problems that occur, we're lucky to make 12 waves a day. And in order to do this study, you'll see in a minute that we make an awful lot of waves. So we didn't want to keep waiting longer and longer. So this was decided to be a reasonable amount of time to wait. You can see the wave is quite repeatable, but the position of the breaking varies by about 1 centimeter. That's 1 centimeter out of 600 centimeters. So what we did to the data then was to slide the profiles horizontally and a tiny bit vertically to bring them all together at the moment of jet impact. And you can see how well all the profiles collapse, except right here at the jet tip as it's about to hit the water surface. And that's due to an instability in the tip of the jet, as you can see in the white light movies. Again, the weak breaker is the green and the strong breaker is the red. And if you take this alignment and maintain it for all the profiles and go backward in time to the moment of jet formation, then you can see the set of red profiles here becomes this one, which is collapsed well, but not quite as good as it was at the moment of jet impact. So this kind of alignment seems to bring the profiles together quite well. And after this time, all the distances and times are shown as shown here with x minus xib. I won't bother to explain the subscript and the superscript, but this is the distance from the point where the jet hits the water surface. If you look at the three profiles, you can see the red one, they're aligned to have the same height crest, but you can see the red one goes down further to the point of jet impact, and the horizontal distance between the top point on the crest, that's what we call the crest point, and the jet impact point is also bigger. So this wave is bigger in some ways, and I'll talk more about that in detail. So we tried to define parameters describing this wave, and here are some of the ones we found. This is the moment of jet impact. This is the crest point, the highest point on the wave. This is the jet tip formation point. And we defined this height HF, and this distance from the trough point upstream, the lowest point, to the crest point, the horizontal distance is LF. And the F over here refers to the moment of jet formation, and the C, the subscript C, to the crest. And this is the crest speed, U, the crest speed at the moment of jet formation. And then at the moment of jet impact, which occurs down tank a little bit, the crest point is now here, the impact point is here. There's a velocity of the jet tip, velocity of the crest point, and we measured these geometric parameters here. And if you look in the table, you'll see if you look at the wave height HF, or the length LF, or the crest speed, these numbers vary by at most about 10%. And the same is true with the jet impact speed here. It's from 1.87 to 2.05. But if you look at Rx and Ry, these distances here, you'll see that they vary substantially from 57 to 81 and from 53 to 69. And if you calculate the area Qi, it increases by almost a factor of 2. So even though the waves, in a lot of waves, the three waves are very similar, there is a difference. And this difference is what creates, first of all, sort of an impression that what we call the strong wave appears to look stronger, the turbulence looks stronger, and we're trying to kind of measure that. So this is a set of profiles from 10 realizations of the wave at 171 milliseconds after the jet impact for the strong breaker, I believe. And you can see here is the crest of the original wave. Here's where the jet impact came into the water. And this is the first splash that comes up. And now it's splashing into the water surface and about to create a second splash up. You can see that these profiles are very repeatable. And these profiles on this side are very repeatable. But in the middle, you have a run-to-run variation due to the randomness of this turbulent flow in this region. And we tried to make some measures of that. And here on the bottom, the black line is a sketch of what would be the average profile at this point in time. And the thin line is supposed to be one of the profiles that you would get from a realization, but these are just artist renderings. And we measured two things about these profiles. One is the normal distance from the mean profile to an individual profile. We call that N, and that could be measured at any position along the normal profile. And the other is an arc length measure. This thick red line is the arc length of the mean profile, and this SI is the arc length of an individual profile. So in the plot up here, we've taken the variance of the normal distance and plotted it as color along the profile up here. And as you would expect, here where the profile varies from run to run, you have a big variance. So these are true ensemble averages of the breaking profiles. And that's just a mathematical definition of N. Oh, and please don't hesitate to stop me at any point if you have any questions about this. I'd be happy to answer anything, and I prefer, if you don't understand something, you will ask in time to understand the rest of the talk. I'm in.
Yeah, thanks. Just a quick question. So because so far we're just talking about propagation along the x direction, right? So how do you account also for the transverse direction? So how would this affect the results here?
So the only measurements we made were with a light sheet plane in the center plane of the tank in the streamwise direction along the tank. And
I see.
If you made a profile next to it, with another light sheet, then you would have differences at each instant in time from this one, because the turbulence and the free surface are three-dimensional in shape, particularly the small ripples. So,
right.
but on the other hand, every time you make the wave, you're probably at a different place in the flow.
Right.
Because the flow is not the
Of course.
same every time, right?
Of
So
course.
we are kind of moving from one cross stream location to another in a sense by doing that.
And that's how you average basically the profiles, right? Because of that.
We did it 10 times mostly because of how much time it takes to make the measurements and process the data. Yeah.
Sure. Thank you.
Yeah. Yep. Thanks for the question. Okay, so this is a set of profiles, not at 650 profiles per second, but something lower. I don't have the number in front of me. But this plot is a single realization of the strong breaker. And the profiles shown here are just of the crest of the wave, and they're in the reference frame moving with the crest point of the wave at the moment of jet impact. So it has this complicated formula down here. Each profile is lifted up a bunch above the previous one so you can see them all. If we didn't do that, then it would just appear like a big black mass of ink. So, the red triangle follows the highest point on the wave profile. And you can see in the beginning, since we're following the highest point at that speed, it stays in the same place in this coordinate system. But you can see that when the splash comes, after a little while, the first splash becomes the highest point on the wave crest, and it generates a second splash, which becomes the highest point on the wave crest, etc., until here at the final profiles, the highest point on the wave is almost outside of the turbulent breaking region of the wave. So just to kind of explain why that is, the wave breaks, it generates turbulence, which is a vortical flow. These ripples that you see in the surface are probably vortex ripples, not freely propagating waves. And because they're moving with the vertical flow underneath, which follows the fluid, not the propagation of the wave has sort of deposited the energy for this turbulence, and it continues to move through the field. And that's why the crest point keeps moving forward and forward and forward. You can see that it's going a little faster than the initial speed here, because this one position is here at 0.05. A little to the right of 0.05, and that's here. So it's moved up a little bit. So then we took each of those times, the 10 profiles we got from 10 repeats of the wave, and we averaged each profile and got the plot that's shown here. So this is the 10 realizations of this set of profiles averaged. And on top of it in color is the standard deviation of the normal distance. So according to this color bar. So for instance, this is the place of the highest standard deviation here. This is where the bubbles come out of the surface on the back face of the wave and pop. And there's another high region here on the front of the splash, the first splash. And there's some high values in here as well. The green dots indicate the position of what we call the indent. That's the indentation made between the impacting jet or splash and the splash up that comes in front of it. And you can see they propagate. At first, they're moving kind of fast and they slow down and are left behind. And at the end of this one, you can see that's kind of where the bubbles come out. And you can see two more of them. There's a third one in here, which isn't indicated. We're able to see in this roughly 4 cycles of impact and splash with diminishing intensity in the average profile sequence. What this means is when you compare the individual one to the ensemble average, that this whole motion, it has a very strong repeatable component to it. And on top of it, we have these small oscillations. But the basic structure of impact and splash up and impact and splash up exists in every realization. And at least at 10 realizations, the phase jitter in it is not enough to smooth it out very much. So these are contour plots that we get from those measurements. The one on the left is height. So this is our entire measurement region. The last one was a little zone like here, following the wave crest. This is the crest of the breaker here, shown in yellow. It's the closest, 0 is the highest height that the wave reaches. The triangle is the location of the maximum crest point height. And the circle is the location of jet impact. You can see it's 0, 0 on this plot. And the indents that were given by green circles are shown here as magenta lines to give you a relationship to the other one. You can see the wave crest in this coordinate system would time up and X horizontal, streamwise distance horizontal. Things that are tilted are moving downstream when they're tilted this way. So the crest is moving to the left as time increases. And this is the trough following it. And this is the following breaker. You can see that as this amplitude goes down of the main breaking crest, the following wave amplitude goes up. And that's just the nature of these wave packets, which are moving down the tank at roughly the group velocity of the waves. And while the crests are moving at the phase speed, which is twice the group velocity. So they're moving through the packet. So at this point, this wave is at the peak of the packet. And at this point, this wave is at the peak of the packet. Okay, so all the call outs, E, D, C, are at the identical position in all 3 plots. This is the contour plot, again, with the same axes, time and distance along the tank of the standard deviation of the normal distance. And you can see that it has this really kind of interesting pattern to it. It, of course, is high up here at the leading edge of the braking zone and very high here where the bubbles come out of the surface behind the wave. And you can see as the second crest goes by, you get an increase in NSD there and showing a lighter color. And that must be due either to the long wave field interacting with short wave components or the long wave field interacting with the turbulence and changing the wavelengths of the fluctuations and therefore their amplitudes too, or probably really a combination of the two. You can see a lot of high frequency structure in here, which falls off as you come over here. And what we've seen from the flow itself is that this is kind of marking the boundary of the turbulent zone of the wave. where you have high frequency structure as opposed to low frequency structure. And this is probably waves that are now propagating in a different direction than the packet itself. So when you move over, oh, you know, I had this arranged. I did such a great job making them grow so we could see them better. And then I forgot about it. Sorry about that. And then lastly, this is the standard deviation of the arc length. You can see it has a whole different character to it compared to the normal distance. And this was just kind of a new idea we had for processing the data. And if you look at the pattern, you can see that it, generally speaking, it has like these striations in it with this wavy pattern to them. And these, you can see this one is very close to the indentation, which is marked by these 3 triangles. That's the beginning, sorry, this is this line, the end, the middle, and the beginning of this line. So there's the 3 of them here. And so these indentations seem to mark something about how these are structured. A strong area here and a strong area in front of this one and a very strong area here. So we looked at the movies and saw that these little bright dashes and dots are associated primarily with bubbles and high frequency waves that end up momentarily in the light sheet. And what we think is that we're tracking particle motion on the surface of the water. So I don't have the equation here, but we made a little equation with a horizontal oscillation in it at the frequency of the main wave, and also drift downstream to the left in this plot. And we adjusted the parameters in it till it looked pretty much like the striations we see here in the plot. We had a constant drift velocity, which wouldn't really be what's happening here, but we're just trying it out. And you can see that when we do that, we get this fit to it, for at least one wave period, it does look like what we see. And when you look back at the value of drift current you had to use to get that, it's about 15 to 20% of the wave phase speed, which is similar to the drift currents that I've seen in the literature. So that probably is what it is. It has this one up here that doesn't seem to drift downstream. And we think these are bubbles and things that have escaped, or maybe they're ripples due to droplet impacts, and they're not being drifted downstream because they're far behind the turbulence. We changed the reference frame. This is for the standard deviation of the normal distance plot. It's the same data as in the last plot, but it's in the reference frame moving with the crest. So you can see the wavefront is almost vertical here. And we, in this coordinate system, we integrated vertically and we integrated horizontally. And these are integrations in the vertical. And then we divide by this distance. So we get sort of the average standard deviation of the normal distance versus distance this way by integrating in time, right? But versus distance this way. And so you can see what happens. We get these initial peaks in the standard deviation. It's not quite ordered according to the weak strong. This little peak in the moderate breaker is higher than the peak in the strongest breaker, which kind of surprised us. Maybe it's because we don't have enough runs. And then as the second wave crest goes by, you can see the smaller peak in the standard deviation. And this is the same kind of phenomena shown in the standard deviation of the arc length. And this guy over here, I believe, has to do with the closing of one of the indentations, which I'll talk about in a minute. And finally, about the surface profiles, we measured an average level of the standard deviation of the normal distance. And here we take that average, divide it by the wavelength of the gravity capillary wave with a minimum phase speed. That's 1.7 centimeters. And then plotted it versus the area under the jet that I showed you in this diagram, this area here. And you can see that at least for our 3 points, it forms a straight line. Would be that we had a lot of other data, but this data is hard to get. So at this time, this is all we've got. And it does seem to scale well with that. You should be aware, though, that a lot of other parameters also vary linearly with QI, like this length decreases as the breaker gets stronger. And if you plot QI versus LF, it's kind of linear as well. Okay, so then we move on to the droplet measurements. Just want to check my time. And I see I've gone kind of slowly here, I'm sorry. So this is a setup for holographic system. There's a laser over here on the right. It goes through a spatial filter, which makes the beam intensity uniform across the profile, and then through a filter to cut down the power, through a collimating lens, and then it shoots across the tank, which is 1.15 meters wide, into the lens of a camera with a long distance microscope lens on it. It's focused in the mid-plane of the tank. And if you look at the holograms that you get from that, if you want to calibrate, what we use is called a reticle. It's a glass plate with black dots and lines on it, and it's carefully calibrated in size. And if you put the reticle in the focal plane of the camera at the center plane of the tank, you get an image that looks like this. All the dots are very sharp, and you can see a dot all the way down to 50 microns with ease. And if you look carefully, you can see one at 100 microns, at 30 microns as well. Then if you take that reticle, don't change anything about the camera system or the lens or anything, and move the reticle over to the sidewall of the tank at a distance of 0.505 meters away from the focal plane, and take the picture again, you get this. And we use digital reconstruction software that was given to us by Joe Katz at Johns Hopkins University, and to reconstruct what this hologram tells us about the object that was at 0.505 meters. So when we reconstruct at 0.505 meters, we get this picture, which shows very sharp black circles where each of the dots was. And if you look at the lower level, you can see as I count over 1, 2, 3, 4, 5, 6, 7. So that's the 100 micron drop. You can even read the symbol over here. But if you look over here, 1, 2, 3, 4, 5, 6, 7, that's where it is. And it's able to reconstruct this and show that what it's taking a picture of is a black dot of 100 microns in diameter. Very sensitive. So we measured holograms all on the same level across the tank. And they are a centimeter above the highest point that the crest of the strongest breaker ever reaches. And at each place, we took a hologram movie. And at each place where we did that measurement, we actually took 10 hologram movies. We used 28 locations with 2 cameras. So 14 different positions for the carriage that moves all the optics up and down the tank. And we did 10 repeats at each place. So 140 braking events for every wave. And this little movie kind of demonstrates that. There's a LIF movie of the breaker on the bottom. And here are shown the location of all the measurements. They're measuring the droplets all the way across the width of the tank at this height. And here, the ones in blue, the movies that come with this for the holograms synchronized with the movie of the wave profile are shown in this little animation. So the wave comes in from the right, and you can see the breaker there and the droplets that are generated going up in the air. Oops, sorry, I must have killed it. Wait a minute. I'll keep my hands off it. So you can see the many droplets in the second window on the right, and then in the middle windows, and then later downstream in the later windows as this breaking crest goes by. So the profiles and the droplets are all synchronized, as are the locations where we took these measurements. In each sequence of images at 650 holograms per second, these are all the droplets in this run that were that moved into the field of view by coming up across the lower boundary in red in the middle of the image, this guy over here. So droplets that come in here or come down here, we don't bother with those. They came from some other measurement location. We want only the ones coming up in the air from this one. And they're coded according to droplet size, is the same as the droplet symbol. And black is early in time and the colors are later. So for instance, this one is going to the right and down again. Well, this one is going to the left and down again. This one is going way up in the air through and then coming back down again, we think. Actually, we can kind of measure it up here. And so we get all those tracks, and what we record is the diameter, position, and velocity of the droplet as it passes through the measurement plane, which is this red line. And when you take all that data and make, again, a contour plot, this time for the number of droplets on the time and the position, you get these two peak zones where most of the droplets are produced. This is the weak breaker, and over here, the stronger breaker. And you can see these two locations where you have the strongest drops. They're easier to see here in the strongest breaker. This one is not the bubble popping zone. That's kind of over here. And I'll talk about that in a minute. And this over here is the set of profiles that I showed you before for the ensemble average of the strongest breaker, but now they're shown in a reference frame fixed in the laboratory. So the crest point is moving to the left along these green dots. And over here is the same set of profiles, but on top of it are dots showing the location of a droplet that was measured and the diameter of it coded in color. And the blue color is the smallest ones and the yellow color the largest ones. And this is where the bubbles come out of the water surface, but this is where there's a lot of droplets. This is the closing of this indentation. And it's a significant thing. First of all, actually, I forgot to say, this is from 3 runs, not 10. If we put all 10 on, it's just so many droplets, you can't really see any details. And here is a couple of movies to show you what's happening. So this is one view with the camera sort of high and looking down, and you can see the splash up, and you'll see a few droplets come out in the foreground of the image, and then bubbles come out across here. And then here's another indentation up here with more bubbles. And then if I do the same wave again, but this time with the camera lower, looking more horizontally, and you'll see the jet impact occur, the splash up. And then right about now, you see a whole sheet of droplets come up. That's that first zone of a lot of droplets. And then you see a lot more on the front face. I'm sorry, these are a little dark. And then this is from underwater with the same wave again. Looking up, this is the back face of the wall. Here's the bubbles from the turbulent zone. These are the bubbles that were under the crest. And then right at the end, they separate. That's when the cavity closes up. And then later, these bubbles come to the surface and pop. So,
sorry, James, can I interrupt?
Yes, sure.
Yeah, sorry, just a short question. So this depends also obviously on the velocity of the waves, right? Or the frequency adopted here.
Yes.
Right, I see. And another question, I mean, this depends also on the viscosity, right? So, and surface tension, surface tension. And so you really assume that the water has to be really clean, right?
So in this case, it is. We measure this. We take samples of the water every day in the morning and the evening. and we put it in what's called a laminar trough, which has a surface tension measuring device in the middle. And it has two barriers. Whoops, always have trouble looking at myself here. And they come together with a surface tension device in the middle over a period of about 30 seconds. And they compress the surface, increasing the number of molecules per unit area. And when you measure clean water surface tension in water, it may actually have a lot of surfactant molecules on the surface, just not enough to make the surface tension go down. But we make sure that we can always compress the surface by a factor of 4 and have the surface tension still be 73 dynes per centimeter. So it is really carefully done, as best you can do in 10,000 gallons of water.
Definitely.
It's a lot. It's a lot of water.
It's good that you have the filter, because sometimes you just leave the water just overnight, you come back the next day, like some oil
like,
or whatever on it.
Yeah, like soup. Yeah, it's really
exactly
really bad.
Thank you, Ryan.
Yeah, sure. And so this is number of droplets versus position. They were integrated over time, like the surface ripples were. And you can see when the first crest comes by, you get a lot of droplets. You get many more for the strong breaker, and the weak one is less. And when the second crest comes by, it's not as ordered as that. Actually, the moderate breaker is giving the most number of droplets. And we took all that data and we made a probability distribution of the droplet size, shown here, droplet diameter on the horizontal and probability on the vertical. And the strong breaker in red. We get this kind of structure with the two straight lines. And we did a function fitting thing to find where the break and slope is. And that's shown here. That's the radius for the break and slope. It increases with breaker strength. The coefficients for the power law fits have a less clear trend to them. There are, we definitely can see the green dots lower than the blue, which are lower than the red. So it looks pretty good. I intended to put a plot here of a theoretical distribution from bubble popping on top of this, but I haven't been able to do that yet. So I plan to do it soon. If you break up the droplets into 3 regions, this is from the closure of the first indent, which produces that sheet of droplets that flies in the air. Then these are, there's fewer drops, so the curves start looking wiggly. And but you can see a general trend here with the stronger one producing more drops in that region. And then over here is all the drops produced on the second crest. And these are almost on the same curve. That's probably due to it all being due to bubbles that come back to the surface sort of slowly and reach the surface and then pop. And maybe the density of bubbles coming up and the size of bubbles is pretty similar in that case. If you look at the total number of drops shown here in the bottom line, then you see, that the number of drops increases from the weak to the strong breaker by a factor of a little less than 2, just like the roughness did in this case. And that seemed pretty exciting. And I won't have time to explain this, but just to show you the plot. These are diameter in the vertical versus time in the horizontal for the 3 waves, the weak, the strong, the moderate, and the strong. And on the vertical axis is diameter, and the color is the number of drops. So you can see there are many more small droplets, particularly over here in the strongest breaker. This is the peak due to the cavity closure, the indent closure, and this is the second peak. That seems to be kind of a combination of the bubbles popping on the back and bubbles popping on the front face of the turbulent zone. And then finally, this is the plot that I showed you earlier with the standard deviation of the normal distance normalized by the wavelength of the minimum phase speed gravity capillary wave. plotted versus the area under the plunging jet. And these are the numbers of droplets versus the area under the plunging jet. This is the total in the blue line here, showing it too is pretty linear. This is all the ones on the breaking crest, and this is the ones on the second crest, which don't seem to change that much. So I wrote a few conclusions here about how repeatable the profiles are, except for this fluctuation due to the turbulence that impact, and that the primary sites of high standard deviation and droplet production are where the crater closes. Actually, there's not that high a standard deviation in N where the crater closes, but the location where the air cavity entrapped under the jet comes to the surface has a high droplet production and a high standard deviation. And the spatially and temporally integrated surface normal fluctuation scales linearly with the area under the jet's upper surface at impact, and so does the number of droplets produced. Well, I'd be happy to answer any questions. Now I'll leave the screen up in case.
Okay, thank you very much, Dr. Duncan. Very
You're welcome.
interesting presentation. I'm always impressed by very beautiful pictures and movies. Thank you very much.
Thank you. Thank you.
Now let's open questions and comments from audiences. Do you have any questions? Okay, so may I ask questions? The first question is about how to generate breaking waves. You use dispersively focused wave packets. It means starting from high frequency waves, namely slow waves to low frequency waves at high speed. So
yeah.
How do you control? I think I guess the waves are controlled such that all waves converge at one focal point.
Yes. Yes.
So
yes.
Then
by linear theory.
By linear theory. So
yeah, I mean, it's not that's not really what happens, because it's nonlinear. But we use linear theory to write the code that runs the wave maker. And if we tell it to break at 6 meters downstream, it ends up breaking at 5.7 meters or something like that.
Okay.
Yeah, a little bit early.
So you said the second wave is coming. So what is the second wave? It's always.
So let's suppose I make a wave packet that doesn't break. Okay, so I run the wave maker, and when the wave maker is finished, I see, let's say, 5 wave crests in the tank. And the wavelength between the first 2 is short, and then the second and third is longer, and the third and fourth is longer, and the fourth and fifth is even longer than that. So the wave energy in the back of the packet is moving faster than the wave in the front. And if I follow the wave packet down the tank, pretty soon I'll only see 4 waves, and then later only 3, and then only 2, and then sort of 1. But if the envelope of the packet, a line that went from crest to crest, and one that went from trough to trough, and that forms the envelope of the packet. And inside the packet, the waves are moving through the envelope.
Okay, I see.
Because their crest velocity, their phase velocity is twice the speed of the envelope. Because they're deep water gravity waves. The envelope's moving at the group speed, and the wave crests are moving at the phase speed, which is twice as big as the group speed. So when it reaches the middle, this packet will invert when it comes out. When it reaches the focal point, it'll come out, and then you'll see 2 waves, and then 3 waves, and then 4 waves, and then 5 waves. And the order will be different. The first wave will have a long wavelength, and the last wave will have a short wavelength. Because they inverted. And so when we make this packet, when one of the crests, you arrange it so when the envelope is the smallest, in width,
Mm.
there's a crest at the peak of the envelope. And that's the one that's going to break. Right. And so after that wave breaks, it generates other wave components and things, but still the basic packet is inverting itself. And now it's going to be two waves, and you're seeing the kind of the formation of the second wave.
Oh, okay.
And also it's, it's tailing off. I don't know if it's asymptotically or whatever, but there's wave energy back there. It's just not very big. So when it focuses, there's sort of like a wave and a half in the tank. And after the breaking crest goes through, you start to see the crest of the second wave.
Ah, okay.
Yeah.
Thank you very much. Now I got it.
You're welcome.
Touching on that, were you able to observe any recurrent breaking? Or is it just one breaking and it's done?
So this is something I forgot to say. So the weakest breaker is such that if you decrease the amplitude of the wave maker motion, it'll start to look like a spilling breaker.
Oh, yeah.
And the strongest breaker is such that if you increase the amplitude of the wave maker motion, the wave will break one wavelength upstream.
Yep.
The previous crest that went through the peak in the packet will be strong enough to break.
Yep.
So with it, the way we have it, we only get this one breaking event.
Yeah, I see. Yep.
Yeah.
But it is in a sense possible if you consider a wave group motion, exactly what you described, the different, the phase speed being half the group loss. You have the next one coming through, and it will break as well if there's still energy, of course. Yeah.
And particularly if you make the breaking weak.
Yeah, exactly.
If you back off on it, then I've definitely seen, like 3 crests break in the tank. We just sat, spent hours trying to get
imagine that
right motion. And you after you make a wave, you have to wait 20 minutes or half an hour to do the next one.
Of course.
By the end of the day, you can't remember what waves you made.
Of course.
So
Okay. Yeah. All right. Thank you very much. Thank you.
You're welcome. You're welcome. Thanks for the questions.
Okay. I have another question about the scale effect. When we extend these results to ocean waves, real ocean waves, we have to look at the scale effect. And I'm most interested in the results of diameter probability distribution of droplets. And can we extend this result to the real ocean waves?
What I've always wanted to do and haven't done yet was to do the same experiment with a shorter wavelength than 1 meter that we have now, and with a 2 meter wavelength, to at least have a few points indicating what might happen at larger scale. But to give you, I have a picture of waves at the beach. But so this isn't really the same thing, but it does kind of illustrate something. So it's I have to stop the share and share my entire screen because I have it on here as a background. So let me close all this.
Okay.
And I was afraid you guys were on WebEx, which I've never used before. And this can go to, close and close. So I took this at the beach on the East Coast of the United States. And this is the sand coming in here. And look at what's happening to this jet as it comes down. It's got droplets shearing off the jet everywhere. And it's not a very windy day, as you can see by the what's going on back here. But I guess that in this case, where the wave height is probably 3 feet, a meter, instead of in the lab, it's 0.12 meters, that the jet's falling fast enough that the relative motion between the air and the water is shearing droplets off the surface. And that's not in my experiment. Yeah. So I know there are effects occurring at larger scale. And I consider ours experiments to be the next step in laboratory experiments about these. You know, the theories of droplet production are all based on experiments where there's a little tank of water and they have a little needle in there and it generates a bubble and it comes to the surface and pops and makes droplets. And from that, there's kind of a theory of the droplet production and breaking waves. And I thought that we could, you know, bring it a little closer to reality at laboratory scale. And maybe somebody will, you know, start making the same measurements in a large facility with 5-meter wavelengths and things. That would be great. I know there's one group that's trying, but I don't know if they published yet.
Okay.
Yeah.
Okay, thank you. Thank you very much. Okay. Okay, so any other questions?
May I ask you a question?
Yeah,
Sure, yes, yes.
And thank you very much for your presentation. And I'm also very impressed by your very beautiful pictures and movies of experiments.
Thank you.
Yeah. And I want to ask you about the droplet trajectory. Probably you showed the droplet trajectory on page 19 or 20. And,
yes.
And probably some of the droplets.
Do you mean this slide?
Yeah, this one. Thank you very much. And some of the droplets looked going forward first, but from the middle, the droplet, some of the droplets changed the direction and backward. And what is the external force that make that?
We think so. Yeah. So we wondered about this too. Let me see if I can find my slide. Can you see this one? Okay, I'll make it bigger. It's an early slide that we had. So this is the weakest breaker, and these little dots are the droplets where we measured them and when we measured them. So and so these are coming up across the measurement plane. And then we decided that maybe we could make a model to show where the droplets actually came from, because you know we're measuring up here and they're being generated down here and they have to fly up there. And so we tried a ballistic trajectory model. So we knew the surface profile at the instant in time when we measured it. When we measured the droplet, and we also, sorry, why did I lose it? Wait a minute. And we also, I don't know, come back here. Oh, there they are. And we also know all the profiles forward and backward in time. So we use the ballistic trajectory model to find out where it left the surface, right? And no wind, just like a particle in a vacuum. And when we do that, that's what we get here on the right. This is the location of all those droplets on the left when we track them back in time to see where we think they came from. And look, a bunch of them come from the smooth water surface ahead of the wave, which shouldn't be, you know, there's no bubbles or anything up there. And it must mean that there's an air flow field that's interacting with these very tiny droplets and moving them around. And I think that's what, you know, there's vortical motions up there. And I think that it's changing the trajectory of the droplets. And that's one of the things we're hoping to get from the CFD calculations that Liang Shen is doing.
Okay.
Good question though. We noticed that too. It was really kind of shocking You know, at first I thought that the student didn't know what he was doing, but it looked good. It looks good. We have these plots that I didn't show here, showing the direction that the droplets are going. So this is the number of droplets, and this is sort of a boundary of all the droplets for the weak, moderate, and strong breaker, and they're heading downstream and up on average, but not all of them.
Yeah.
Yeah.
Thank you very much. Yeah,
Oh, you're welcome. You're welcome.
interesting. Yeah.
Another good question. This is great.
Thank you.
Okay, thank you very much. Any other questions? Okay, thank you very much, Dr. Duncan, again for
Okay.
lecture. Thank you very much.
Well, you have a good day. Thank you so much for inviting me. It was
Thank
fun.
you. It's a public holiday. It's a public holiday today, so that's why
Oh,
we're all
is it?
sitting at home.
I know why I'm sitting at home, because it's after dinner. Oh, okay.
Thank you
All
very much.
right.
Thank you.
Okay.
Thank you. Take care.
Thank you
Bye-bye.
very much. Bye-bye.
Thank you. Bye-bye.
Bye-bye.